This is lecture number 36 of our course on fundamentals of transport processes. Welcome to this lecture. We started off this course by deriving the mass momentum conservation equations, the Navier-Stokes equations for flows of Newtonian fluids. And the momentum conservation equation contains a balance between inertial and viscous forces. And as I said, the momentum conservation equation is in general a nonlinear differential equation. So, there is no general procedure which can be used to solve these equations for all situations. One needs to make approximations depending upon the situation under consideration in order to solve this equation. In the previous lectures, we had looked at different approximations that could be made based upon physical considerations, based upon the ratio of inertial and viscous forces. The momentum conservation equation basically balances the inertial and the viscous forces in the fluid. If the inertia is small, then there is a dominance of viscosity. Therefore, diffusive effects are dominant compared to convective effects. And we looked at ways to solve the equation when the flow is diffusion or viscous dominated. In that case, the equations mostly reduce to Laplace equations, which could be solved by a variety of techniques. Next, we look at inertial dominated flows. When we looked at inertial dominated flows, first of all, we made the approximation that the flow was inviscid. That means that the viscosity is equal to 0. The second was irrotational, that is, there is no vorticity anywhere within the flow. An important approximation, irrotational. And if you assume that the flow is inviscid and irrotational, then one derives the potential flow equations for the Navier-Stokes equations reduce to the potential flow equations. Because the flow is irrotational, the velocity can be expressed as the gradient of scalar velocity potential, because the curl of the velocity is equal to 0. And the vector momentum conservation equation just reduced to the scalar Bernoulli equation for the pressure. And these simplified equations were solved subject to boundary conditions. Of course, since we have neglected the viscous terms in the conservation equations, we can no longer satisfy all of the boundary conditions. When we neglect the viscous terms, we are neglecting the shear stresses exerted by bounding surfaces on the fluid, because the shear stress depends upon viscosity. So, one can have only pressure forces acting within the fluid. For this reason, one can satisfy only the normal velocity and the normal stress boundary conditions at the surfaces. It is not possible to satisfy the tangential velocity and the tangential stress boundary conditions at the surfaces in potential flow. So, we looked at how to solve the potential flow equations in various situations, both 3 and 2 dimensional. And in all of these cases, the simplification made was that the flow was there was no tangential stress at the surface, and therefore, we could satisfy only the normal velocity and the normal stress conditions. However, in a real situation, the velocity does in fact have to come to 0 at bounding surfaces, because in the physical situation, the no slip condition has to be satisfied at the surfaces. And that led us to the analysis of boundary layers, thin layers near surfaces where viscous effects continue to be of equal magnitude as inertial effects, even in the limit as the Reynolds number goes to infinity. So, there is convection that is taking place in the streamwise direction. Okay, the simplest boundary layer that we looked at was the boundary layer for the flow past a flat plate. The simplest one that we looked at was the boundary layer for the flow past a flat plate. Okay. Now, you had a velocity, a constant velocity u coming in, and there was a boundary layer here. This is the streamwise direction, the cross stream direction. Okay. If you just use the outer potential flow, that would predict that the velocity is equal to capital U everywhere. However, that does not satisfy the no slip condition at the surface of the plate itself. and for that reason you have to incorporate the viscous effects within a boundary layer of thickness, okay, delta, which is small compared to the length scale of the flow. Okay. This thickness delta is dictated by the flow itself, because the only way that the velocity will come to 0 at the surface is if there is shear stress at the surface. The Reynolds number based upon the macroscopic length scale L is large. Therefore, you cannot have a balance between inertia and viscosity over length scales comparable to capital L. Okay. However, if there is a velocity gradient in the flow very close to the surface over a very small thickness delta, delta being small compared to L. Okay. So, the velocity starts from 0 at the surface and reaches the free stream value of or reaches close to the free stream value of capital U within a layer of thickness delta, and delta is small compared to L, then the velocity gradients are much larger than you expected based upon the simple scaling of the velocity and the length scale L. Because delta is much smaller than L, the velocity gradient is much larger than U by L. And in that case, one could have a balance between inertial and viscous forces provided delta is small enough. How small does delta have to be for the balance between inertial and viscous forces to be for viscous forces to be comparable to inertial forces even as Reynolds number goes to infinity. Okay. We found that delta by L has to be proportional to the Reynolds number power minus half. So, this is a length scale that is set up by the flow itself, by the requirement that the only way that the velocity is going to come to 0 is if there is a balance between inertial and viscous forces within a thin region. And then in order to obtain similarity solutions, we use the additional piece of information that at a given location x within the flow, the value of the boundary layer thickness at that location will not depend upon the total length L, because the downstream edge of the plate is downstream of this location x. So, at a given location x, the only length scale that is relevant is x itself, which is the distance from the upstream edge, because convection is transporting momentum downstream. Therefore, any boundary conditions that are applied at a downstream location to this point x cannot affect the flow at the given location x. And using that additional piece of information, we had managed to find similarity solutions for this particular case, and there were other cases for which we managed to find similarity solutions. Okay. For any velocity profile for which u is proportional to x power beta, u, the mean velocity, varies as some power of x. In this particular case, beta is equal to 0. Okay, so, the mean potential flow velocity varies as x power beta, does admit a similarity solution, and those were known as the Faulkner-Kahn solutions. This is a family of solutions for the flow, for the potential flow in a corner. Okay. For the potential flow in a corner of angle pi by m, okay, where beta is equal to m minus 1. Okay. So, for all of these flows, it is possible to get similarity solutions. Okay. And we found out the scaling of the boundary layer thickness, the shear stress, and so on, depending upon this parameter beta. It is only for this class of solutions that we got boundary layer, this class of potential flows, that we managed to get boundary layer solutions. But this gave us additional insight into the dynamics of the flow. Okay. So, if we plot, for example, as a function of this downstream distance x, right, we have a boundary layer here, okay, and this boundary layer thickness delta depends upon x. Okay, we had derived the scaling between delta and x It depends upon whether the flow is accelerating, decelerating, or is a constant. Okay. Delta was basically equal to nu x by u of x power half. Okay. That was the scaling for delta, okay, at a given location x. Okay. And of course, u goes as x power beta. So, there is a dependence of delta on beta as well. So, what we found was that if x is equal to if beta is equal to 1, okay, if beta is equal to 1, which corresponded to a stagnation point flow, we found that the boundary layer thickness was a constant. Okay. It was independent of x. That is because the flow is being accelerated downwards. For this particular flow, ux in the potential flow, okay, you find that ux is proportional is equal to some constant times x. Okay. So, it is accelerating downstream. The boundary layer thickness is constant. For the flow past a flat plate that we done earlier, we found that delta was proportional to x power half. Okay. So, it increases as you go downstream. If the angle is less than 90 degrees, as in this case, as I have shown here, the angle is less than 90 degrees, the boundary layer thickness actually decreases as you go downstream. The boundary layer thickness decreases, whereas if greater than 90 degrees, then the boundary layer thickness increases as you go downstream. Okay. In all these cases, we managed to get a similarity solution. Okay. The solution was always of the form, we wrote a stream function of the form nu x f of eta, where eta is equal to y by delta of x. Y is the cross stream direction and x is the streamwise direction. Okay. And on this basis, we found the velocity ux is equal to u of x times f prime of eta. Okay. There should be no nu here. Okay. Delta u times f of eta, okay, was the stream function, where delta is the boundary layer thickness. On that basis, ux was equal to f prime of eta. Okay. And this gave us a very important insight, okay, and that was that the velocity profile ux by u, which is equal to f prime of eta, if you plot that as a function of the similarity variable eta. Okay. Of course, for the free stream, this f prime has to go to 1. Okay. In the limit as eta goes to infinity, this f prime has to go to 1. The profile, of course, depends upon beta. Okay. So, for example, for the Blasius boundary layer, for the flow past a flat plate, okay, beta is equal to 0 corresponds to this profile that I have here. Okay. If I increase beta, that is, if I go to the case where I have a stagnation point flow, you will get a similar velocity profile, okay, except that it will reach the free stream value faster. Okay. Beta is equal to 1, which corresponds to the flow past a flat plate. It corresponds to something that looks like this. Okay. So, as beta increases, the gradient at the origin of the velocity increases, or the shear stress at the origin increases. As beta decreases, the gradient decreases. Okay. If you decrease beta below 0, you find that at some point, okay, so at beta is equal to 0.5, it looks like this. Okay. You reach a point beta is equal to 0.090 minus, I am sorry, I should write this as minus 0. At beta is equal to minus 0.05, you get something like this. Okay, beta, and you reach a point where beta is equal to minus 0.0904. Where the slope of this curve at the origin is equal to 0. That means that the derivative of the velocity with respect to the y coordinate is equal to 0 at that point. When the derivative of the velocity with respect to the y coordinate is equal to 0, that means the shear stress is equal to 0, because tau xy is equal to mu times dux by dy. Okay. And at that point, the velocity becomes 0, the slope is 0 at the origin, If you decrease beta further, you end up going in this direction. Okay. That means that if you decrease beta further, you will end up with a small region where there is velocity in the opposite direction very close. Okay. This corresponds to a recirculating region, and we have drawn the analogy between this and the flow past a sphere. We had taken the flow past a cylinder in the last lecture. One can do a similar calculation for the flow past a sphere, but let us just stick to our example of the flow past a cylinder. Okay. So, as this potential flow streamlines go around this, the potential flow streamlines are of course symmetric. Okay. If there is no circulation, the potential flow streamlines are symmetric. Okay. At this front edge, what you get actually corresponds to beta is equal to 1, because that corresponds to a stagnation point flow. Okay. If you expand this region out, okay, it corresponds to a stagnation point flow. Okay. So, here there is an accelerating streamline, the velocity is increasing as the distance along the surface increases. Okay. So, it corresponds to a stagnation point flow. As you go downstream, if you reach the top and bottom surfaces, you will find that at these 2 points, the flow resembles just the flow over a flat plate. The flow resembles the flow over a flat plate for which beta is equal to 0. Neither any acceleration nor any deceleration. Okay. So, the velocity profile, okay, at this surface will look something like this. Okay. As you go downstream, the flow actually decelerates. On the upstream side, because the fluid has to go around the cylinder, the flow accelerates. On the downstream side, it comes back down because it has to fill in the volume that is behind the cylinder, and the flow decelerates. And in this decelerating flow, at some point beta becomes equal to minus 0.0904. Okay. At some location here, okay. At some location here, beta becomes equal to minus 0.0904. That means that at this location, the shear stress itself at the surface is equal to 0. Okay. And if you go a little further downstream, okay, beta becomes less than minus 0.0904, and you end up with a recirculating region. Okay. Very close to the surface, the velocity is actually opposite to the free stream velocity. Okay. You end up with a recirculating region. Okay. So, you have a second point here, okay, a second point here corresponding to this point here, at which the velocity is equal to 0. So, you have 2 points at which no slip is satisfied. That means that the second point also acts something like a surface with a zero velocity condition. Okay. That there is the tangential velocity comes to 0 at this point. The normal velocity of course is equal to 0 because it is perpendicular to the streamlines. And this region behind is what forms the wake. Okay. And you have recirculation within the wake. Okay. So, even though the potential flow predicts that the velocity is symmetric, because the boundary layer separates on the decelerating side, you end up having a wake behind the cylinder. Okay. In this wake, vorticity effects are not small. The pressure within the wake is much smaller than the pressure in the potential flow, and for that reason you get a net force. When we calculated the force on the cylinder, we found that it was 0 in the absence of circulation. That was because of symmetry. The pressure in the Bernoulli equation was proportional to half rho u square, and u square on the upstream and the downstream sides in potential flow are the same. Unit normals are in the opposite direction, so there is no net force. The boundary layer theory is telling us that when the flow decelerates on the downstream side of the cylinder, there is boundary layer separation, and the potential flow solution is no longer valid. There is a wake region at the back where there is recirculation. In this recirculating region, the pressure is much smaller than it is on the front side of the wake of the cylinder, on the upstream side of the cylinder, and for that reason you will have a net drag force. In these kinds of objects in which there is boundary layer separation at the back are often called as bluff bodies. Whereas objects that are designed in such a way that there is no boundary layer separation Okay, they are designed to be aerodynamic in shape, so that there is no boundary layer separation. Okay. These are often called as slender bodies. So, that is the distinction between bluff bodies and slender bodies. Slender bodies are designed such that under normal circumstances there is no boundary layer separation on the downstream side. That means you have to make sure that the deceleration is never too large. Okay, so that the beta in the Faulkner-Skan solution never goes below minus 0.0904. Okay. So, this tells us that even though potential flow may predict solutions, they are not always valid, because potential flow solution will be valid in most of the flow only if the regions where the viscosity becomes important are restricted to thin regions near surfaces. In bluff bodies like cylinders or spheres, of course, on the upstream side it is restricted to a thin region. The thickness of course goes as RE power minus half. However, on the downstream side, because of boundary layer separation, it is no longer restricted to a thin region. Okay. And therefore, you do have viscous effects being important within the wake region behind the object after boundary layer separation has taken place. The flow in the wake is of course usually turbulent, and we will come back to analyze what are turbulent flows. But in the meanwhile, it is useful to look at the dynamics of vorticity, okay, in these flows, because usually turbulence usually involves a lot of vorticity intensification due to stretching and bending of vortex lines. Okay. So, we will pause briefly to look at vorticity dynamics in an otherwise potential flow. When we solved the potential flow equations, we made the implicit assumption that it is irrotational, there is no vorticity. There could be vorticity, however, and as you can see here, vorticity, the circulation that we see behind the object, is actually generated at solid surfaces. Okay. The circulation that we saw in the wake region is actually generated at boundary surfaces. Okay. So, we will look at vorticity dynamics. How does vorticity convect and diffuse in flows, and how is it generated at surfaces? Okay. So, that is the next topic, vorticity dynamics. So, first things first, we can write an equation for the vorticity. Omega I is equal to epsilon I j k partial u k by partial x j. Alternatively, omega is equal to del cross u. The definition of vorticity. Okay. As you know that this satisfies the Stokes theorem, or the theorem for the curl, the integral theorem for the curl, integral dx dot u is equal to integral over the surface of n dot del cross u. Okay. This is also integral over the surface of n dot omega. Okay. So, if I have some surface within the flow, if I have some surface within the flow, so this is the surface S, and this is the closed contour C, which is the perimeter of the surface. Okay. So, integral over this closed contour C, okay, the integral over this closed contour C of the displacement element, the vector line element dotted with the velocity, has got to be equal to integral over the entire surface of n dot omega. If you recall, our Navier-Stokes momentum conservation equation can be written as partial ui by partial t plus uj partial ui by partial xj is equal to minus partial p okay. We will take the curl of this to get the vorticity equation shortly, but first we can just note that many of these terms in this equation can actually be written in terms of the vorticity. Okay. In particular, if you take this diffusion term here, if you take the curl of the vorticity, okay, if you take the curl of the vorticity, epsilon I j k partial by partial x j of omega k okay, that is the curl of the vorticity, and omega can once again be expressed in terms of the velocity, okay, which is equal to epsilon I j k partial by partial x j of epsilon k l m partial u m by partial x l. Okay. So, that is the curl of the velocity. I use different indices in the second term here just to make sure that we do not confuse. I have already used I and j in the first curl. Okay. This epsilon I j k times epsilon k l m can of course be written in terms of delta functions. Okay. So, this can be written as delta I L delta j m minus delta I m delta j L to partial by partial x j of partial u m. So, this can be written as partial by partial x j of partial by partial x I u j minus partial by partial x j partial by partial x j of u I. Okay, just simple algebra. Okay. In the first term, I can change the order of differentiation because the gradient vectors are independent vectors. So, this just becomes equal to partial by partial x I of partial u j by partial x j minus this is just partial by the gradient dotted with the gradient. So, this is just partial square u I by partial x j square. Okay. This first term is 0 because of the incompressibility condition. Okay. This first term is 0 because of the incompressibility condition. Therefore, the Laplacian of the velocity can be written as the curl of the negative of the curl of the vorticity, because I get the curl of the vorticity is equal to minus the curl of the vorticity that I started off here is equal to minus partial square u I by partial x j square. Okay. So, this can also be written as minus nu times del cross omega or epsilon I j k partial by partial x j of omega k. Okay. For the pressure, I need a 1 over density here. So, please note that correction. This is equal to minus 1 over rho times partial p by partial x I. Okay, plus. Okay. I can also write this u j partial u I by partial x j in terms of the vorticity. Okay. We had done that previously when we actually derived the potential flow equations. Okay. We will just do it here quickly. Okay. If I take u cross omega, okay, u cross omega is equal to epsilon I j k u j omega k. Okay. U m, I am sorry. Just writing omega k as epsilon k l m partial by partial x l of u m. Okay. So, this is equal to epsilon I j k epsilon k l m u j partial by partial x l of u m. Okay. Once again, we write epsilons in terms of our familiar deltas. Okay. This is delta I L delta j m times and I can write this as so what this implies is that the convective term, okay, u j partial u I by partial x j is equal to minus And you recall that uj partial uj by partial xi can also be written as partial by partial xi of half uj square. Okay. So, is equal to partial by partial xi of half uj square minus epsilon ijk uj omega k. Okay. Because uj partial ui by partial xj can also be written as partial by partial xj of half uj square. Okay. So, I can write the left hand side of this also as partial ui by partial t plus partial by partial xi of half uj square minus epsilon ijk uj omega k. Okay. Okay, just using vector identities to simplify terms in the conservation equation. So, this is equal to minus 1 by rho partial p by partial xi plus nu, or there is a negative sign here, minus nu, right, epsilon ijk partial by partial xj of omega k. Okay. So, that is an alternative way of writing the equation, and you can see that the Bernoulli equation actually comes out from here if I take omega as identically equal to 0 everywhere, because these two terms end up becoming 0. Okay. Because the vorticity is 0 everywhere, then these two terms actually end up becoming 0. Okay. And then I end up with the Bernoulli equation for the relationship between the pressure and the velocity, and the velocity and the velocity potential. Okay. This was the procedure we used for actually deriving Bernoulli equation. In that case, we had a body force which we wrote as the gradient of a potential and then included that in the pressure, of course. Okay. But this was basically the procedure that we had used. Now, what happens for the situation where the vorticity is non-zero? Okay, so, that is the next question that we will look at. In that case, one should be able to get an equation for the vorticity by just taking the curl of the momentum equation for the velocity field. Okay. So, I take the curl of this momentum equation in order to get an equation for the vorticity. Okay. Let me start off with my equation in a specific form. Okay. So, as the starting point that I will use will be, rather than using I and j, okay, because when I take the curl I will be using epsilon I j k times partial by partial x j of the momentum equation. In this particular case, I will use the free indices as L and M. Okay. And I am sorry, I will use the free index as k and the repeated index as L and M. Okay. So, I will write my equation of this form. Okay. Partial u k by partial t plus partial by partial x k of half u l square minus epsilon k l m u l omega m is equal to minus 1 by rho partial p by partial x k plus nu partial square u k by partial x l square. So, I will start with my equation of this form. Okay. I have taken this term to be the usual diffusion term, whereas for the convection term I have substituted in terms of the identity that I just derived for you. Okay. This convection term I have substituted in terms of the identity that I have just derived for you. Okay. And I take the curl of this entire equation. Okay. I take the curl of this entire equation. So, I take the curl of this entire equation, epsilon a j k partial by partial x j of the entire equation. Okay. So, let us work out what it works out to term by term. Okay. Epsilon I j k partial by partial x j of partial u k by partial t can equivalent be written, you can now interchange the order of differentiation because time and position are independent coordinates. This is also equal to partial by partial t of epsilon I j k partial u k by partial x j. Okay. And what is within the brackets is only the vorticity. So, this is equal to partial omega I by partial t. Okay. So, that is the first term. The second term is epsilon I j k partial by partial x j of partial by partial x k of half u l square. Okay. Partial by partial x k of half u l square is the gradient of a scalar half u square, okay, the kinetic energy or the velocity square. Okay. You are taking the curl of that. The curl of the gradient of a scalar has to be equal to 0. Okay. The curl of the gradient of a scalar has to be equal to 0. Okay. The next term is epsilon I j k partial by partial x j of, okay, there is a negative sign there, epsilon k l m u l omega m. This term turns out to be important. So, I will spend a little bit of time on this one. Okay. So, I can just write in terms of the epsilons as minus epsilon I j k epsilon k l m partial by partial x j of u l omega m. And I use my identity for the deltas once again. Okay. So, this will be equal to minus of delta I L delta J M minus delta I M. Okay. So, this becomes equal to minus partial by partial x j of u I omega j plus partial by partial x j of u j omega I. Okay. So, I am just expanding out this term here, okay, minus partial by partial x j of u I omega j. And now, I can use the chain rule for differentiation. Okay, I can use the chain rule for differentiation. This is equal to minus omega j partial u I by partial x j minus u I partial omega j by partial x j plus u j partial omega I plus omega I. The last term here, of course, is equal to 0 because of incompressibility. Divergence of velocity is equal to 0 in the Navier-Stokes equations. Okay. This term here, the divergence of the vorticity, okay, the divergence of the vorticity, okay, the divergence of the vorticity is the divergence of the curl of the velocity. You know that the divergence of the curl of any vector has to be equal to 0. Okay. So, this is also equal to 0. Okay. And finally, you are left with minus omega j partial u I by partial x j plus u j. Okay. So, that was the second term that we had there. Okay. The next term, of course, is epsilon I j k partial by partial x j of partial p by partial x k. Once again, the divergence of the gradient of a scalar. Pressure is a scalar. Since we have the gradient of the pressure in the conservation equation, if we take the curl of the entire conservation equation, we will get 0. So, the curl of the gradient of the pressure, and that has to be equal to 0. Okay. And the last term that we had was epsilon I j k. Okay, there was a viscosity there. Let me see. Partial by partial x j of partial square u k by partial x l square. Okay. Once again, you can change the order of differentiation to get nu partial square by partial x l square of epsilon I j k partial by partial x j of u k. Change the order of differentiation to get it in this form. Okay. And of course, you can always do that because you are taking partial derivatives and they commute. Okay. What is in the brackets is of course the vorticity itself. Okay. What is in the brackets is the vorticity. So, this is just equal to nu partial square omega I by partial XL square. Okay. So, putting all these together, we will get an equation for the vorticity, the conservation equation for the vorticity. The first term is partial omega I by partial t plus, there are two terms here. Okay. There are two terms here, uj partial omega I by partial xj minus omega j partial ui by partial xj is equal to nu partial square omega I by partial xj square. Okay. I can take this term to the right hand side. Okay, take this term to the right hand side. The first two terms here are the substantial derivative. Okay, the first two terms here are the substantial derivative. And my final vorticity conservation equation becomes d omega I by dt is equal to omega j. So, let us look at this equation. Okay, the term on the left is the rate of change of vorticity. The term on the left is the rate of change of vorticity in a moving reference frame. It is a substantial derivative of the vorticity. On the right there are two terms. The second term on the right is the usual viscous diffusion. Okay, the viscous diffusion of momentum. If you take the curl of the momentum equation, you just get the viscous diffusion of vorticity. Okay. So, just like this concentration diffusion or heat diffusion or momentum diffusion, in this particular case you do have a viscous diffusion of vorticity as well, and the diffusion coefficient for that is also the kinematic viscosity. Okay. And then you have this other term here. Okay. And then you have this other term here. Okay. This is not a source term, because a source term would be independent of the vorticity itself. It is a term that is proportional to the vorticity vector times the gradient of the velocity. Okay. So, this basically says that there is an increase or decrease in vorticity, and that is proportional to the vorticity dotted with the velocity gradient. Okay. The vorticity dotted with the velocity gradient. To try to make sense of that, one can draw an analogy between the stretching and bending of material lines within a fluid. Okay. So, you have a fluid flow. Okay. And I have some fluid material element. Okay. Let me just. Okay. I have a fluid material element, okay, of distance delta x. Okay. As time progresses, because of the fluid flow, okay, as time progresses because of the fluid flow, this material element is going to stretch and bend. And how does delta x vary? Okay, due to the fluid flow. Okay. You can see that at some later distance, this goes to u at x delta t, this goes to some other location u at x plus delta x times delta t. Okay. And you get a new material element. Okay. The stretching of this material element is something we had seen when we looked at deformation. Okay. The stretching of this material element is something that we had seen when we looked at deformation. Okay. We said that the rate of change, okay, the rate of change of this material element with this respect to time can be written as delta x dot the gradient of the velocity. Okay. The gradient of the velocity is the rate of deformation tensor. Okay. This is equal to delta x j partial ui by partial x j. Okay. This is the rate of change of the material element in a reference frame that is moving with the fluid. Okay. So, as the material element moves with the fluid, one end of the material element moves the distance u times delta t, the other end of the material element moves the distance u plus delta u times delta t. Therefore, the change in that the distance moved, okay, the length of that material element is delta x dotted with partial u by partial x, or the rate of deformation tensor. Okay. The vorticity conservation equation, if I neglect diffusion, is telling me a similar thing. Okay. It is telling me that d omega I by dt is equal to omega j times partial ui by partial xj. Okay. Note the correspondence here between this delta x vector. Okay. This should be delta x I if I write in this notation, and I have omega I here. Okay. And it goes as delta x dotted with the gradient of the velocity. Okay. So, what this is telling you is that vorticity intensification, or the change in vorticity, takes place in a manner identical to the change in the length of material elements. That is, vorticity gets stretched and bent in a manner identical to material fluid elements. Okay. So, that is the meaning of this first term here. Okay. Vorticity intensification due to stretching and bending, okay, due to the mean deformation. Okay. So, this is the additional element. Okay. Unlike momentum, vorticity is not a conserved quantity. Okay. Vorticity could be created or destroyed in a flow, and the rate of creation or destruction is proportional to the rate at which material elements are expanding in the flow. Okay. This rate is also proportional to just the symmetric part of the rate of deformation tensor. Okay. So, let us just look at this. Okay. By partial xj can be written as omega j times Sij plus Aij, where S and A are the symmetric and the antisymmetric parts of the rate of deformation tensor. Okay. If you recall, the antisymmetric part can be written in terms of the vorticity itself. Okay. The antisymmetric part can be written as minus half epsilon ijk omega k. Okay. There is a relationship between the antisymmetric part and the vorticity vector itself. And this second term, okay, omega I Sij is equal to minus I am sorry, this should be omega j. This second part is the cross product of omega cross omega, and the cross product of any vector with itself has to be equal to 0. Okay. So, this is equal to 0. So, therefore, I can also write this as omega j times Sij. Okay. So, this is only proportional to the symmetric part of the rate of deformation tensor. This vortex intensification mechanism is only proportional to the symmetric part of the rate of deformation tensor. Okay. So, my vorticity conservation equation can also be written as d omega I by dt is equal to omega j Sij plus nu, okay, partial square omega I by partial xj square. So, what does this omega j times Sij mean? Okay. This is, as I said, a mechanism for intensification of vorticity due to the stretching and bending of vortex lines. Okay. Let us consider a simple two-dimensional flow. Okay. If I have a simple two-dimensional flow, okay, with some velocity profile, ux, which is equal to a function of y. Okay, ux is a function of y. Okay. That means you have velocity, or even if it were a general two-dimensional flow, it does not have to be unidirectional. Okay. Ux is a function of x and y, and uy is also a function of x and y. That is, there is no variation in the z direction. Okay. Ux is a function of x and y, and uy is also a function of x and y. Okay. That means that there is no variation in the z direction. There's the velocity is purely in the plane of the flow. Okay. So, in that case, it is clear that the vorticity vector is the curl of the velocity. It has to be perpendicular to the velocity vector. The velocity vectors are all in the plane of the flow. That means that the vorticity vector can be only perpendicular to the plane of the flow. Okay. in the plane perpendicular to the ball. Okay. That means that omega vector has only one component which is in the z direction. That means the vorticity vector has only one component which is in the z direction. The velocities are in the x and y directions. The vorticity is only in the z direction. That means that omega j times Sij has only 4 components, Sxx, Sxy, Syx and Syy, because the velocity is 2 dimensional, the flow is only in the x and y directions. Omega is only in the z direction. That means that this term, okay, omega j times Sij is equal to 0 for these 2 dimensional flows. Okay. So, you cannot have vorticity intensification due to the stretching and bending of vortex lines for a 2 dimensional flow, because the velocity vector is in the plane of flow, the vorticity vector is perpendicular to the plane of flow. Okay. The velocity gradient has components only that are in the plane of flow, the vorticity is only perpendicular to the plane of flow. That means that you require a 3 dimensional flow in order to have intensification of vorticity due to stretching and bending of vortex lines. Physically, how does that happen? It is basically a consequence of angular momentum conservation. Okay. So, if I had an element of fluid that looks something like this, okay, okay, a cylindrical element of fluid, okay, by volume conservation, if it expands in one direction, it has to compress in the other directions. Okay. So, let us assume that it is expanding in this direction. Therefore, it has to compress in the other directions. Okay. This is cylindrical, so it compresses in all directions around the cylinder. Okay. Okay. It compresses in all directions and it expands in only one direction. Okay. So, this stretching will make this volume element, okay, greater length, okay, and smaller diameter. Okay. Greater length and smaller diameter. Okay. Note that this is a 3 dimensional process. This compression in 2 directions and expansion in the other direction. And let us further assume that the vorticity is along the direction of expansion. Okay. So, let us just put an x axis here, okay, and let us further assume that it is circulating in this direction. Okay. So, that the vorticity omega is equal to omega x Ex. Okay. Now, you can see that between these 2 configurations, the angular momentum of this parcel of fluid is half I omega square. Okay. The angular the angular momentum of this element of fluid will be equal to L is equal to I times omega, okay, where I is the moment of inertia. Okay. When you go from this larger on the left hand side, from this larger to the smaller on the right hand side, if the angular momentum is conserved, the moment of inertia has decreased, because the moment of inertia is proportional to half m times r square, where r is the characteristic distance, the length of that cylinder. I has decreased, therefore, the vorticity has to increase. Okay. So, stretching it along the direction of vorticity will basically increase the vorticity, compressing it along the direction of vorticity will decrease the vorticity. Okay. So, for vorticity that is already present in the flow, if you stretch it, you will increase the vorticity, and if you compress it, you will decrease the vorticity. The fact that vorticity intensification or the rate of change of vorticity happens in a manner similar to the length of material lines is also reflected in a theorem called Kelvin's theorem, which basically states that that the vorticity along a moving line element has to remain a constant. Okay. So, this is Kelvin's circulation theorem. Okay. If you take the time derivative of the vorticity along some loop within the fluid, okay, this loop is a moving loop. Okay. So, it moves along with the material line elements. Okay. It goes to from at one time it is here, at t plus delta t it goes to some other location. Okay. This I can write it, I mean there is 2 reasons why the circulation changes along this loop. One is because the velocity itself is changing. The second is because the line element itself is changing. Okay. So, let us just write it in initial notations for in order to make it clear, dxi ui. Okay. So, because the velocity is changing, there is a rate of change, okay, dxi dui by dt. Okay. And also because the line element is changing, dxi is equal to, okay, the rate of change of this line element is dxj times partial ui by partial xj. Okay. So, that is the rate of change of the line element. Okay. Delta xi is equal to delta xj times partial ui by partial xj, the rate of change. Okay. Just the relation that I just used. Okay. So, this is equal to integral dxi, okay. dui by dt is minus plus integral dxj of ui times partial ui by partial xj can be written as integral dxj of partial by partial xj of half ui square. Okay. So, just simplifying this term, I have ui times partial ui by partial xj, which I write as partial by partial xj of half ui square. Okay. The second term, gradient of a function integrated over a closed loop, has to be equal to 0 from the gradient theorem. Okay. Basically, the gradient of some function half ui square integrated over a closed loop, dx dot grad phi integrated over a closed loop has to be equal to 0. Okay. In the first term, the pressure gradient integrated over a closed loop, once again the gradient of a scalar integrated over a closed loop has to be equal to 0. Okay. So, therefore, you find that the rate of change of vorticity dot u, okay, ultimately just becomes equal to dxi, okay, that is a kinematic viscosity partial square ui by partial xj square, okay, which is equal to the kinematic viscosity times the del square of x. Okay. If you recall, we had also written this as equal to integral dxi of minus nu epsilon I j k partial omega k by partial xj. Okay. Del square u is minus curl of the vorticity. So, what this is telling us is that there is a change in the circulation along a moving material element only due to viscous diffusion only. So, this basically proves the Kelvin theorem that if you have no viscosity in the fluid, then the circulation along a moving material element will not change with time. Okay. So, even though the fluid is, if the fluid is inviscid, you can still have vorticity in the fluid, but that vorticity will be convected downstream with circulation along any loop remaining unchanged as the fluid is being convected. So, even in an inviscid fluid, if you do have vorticity, this is telling you that it cannot be generated, it cannot be produced or dissipated in the inviscid fluid, but just moves along in such a way that the circulation remains unchanged in the flow. So, this is about vorticity dynamics within the flow. Where is vorticity generated? We had seen an example of that for the flow around a cylinder. At the surface, because of boundary layer separation, you have circulation. So, vorticity gets generated at solid walls and then it gets convected through the flow, and if there is viscous diffusion, it gets diffused as well. What is the mechanism of generation of vorticity at surfaces? We will see that in the next lecture. So, we will continue this vorticity dynamics in the next lecture and then move on to our analysis of turbulent flow. We will continue this in the next lecture. Kindly revise the calculations that we did here. I will go through that briefly in the next lecture, but kindly go through and make sure that you understand all of the algebra that is done here. So, we will see you next time.